Every single day, all around us, there's this constant, this ocean of invisible energy, isn't there?
Absolutely. Think about it, the noise of traffic, a bird flapping its wings,
Hmm.
even just typing on a keyboard.
Right. We know sound gives us the sensation of hearing, and we know it's a form of energy, mechanical energy.
And that simple fact immediately throws up a fascinating question.
Hmm.
We know energy can't be created or destroyed, only changed. That's fundamental.
It's the law of conservation of energy, yeah.
So if you clap your hands, you're using muscle power, mechanical energy. The real puzzle for our deep dive today is, what's the story there?
How does that energy transform? How does the clap become the sound we hear across the room?
Exactly. It's like an invisible trail we need to follow.
A bit of a detective story, really.
Yeah.
Following that disturbance right from the start, the source, to the finish line, our eardrums.
And our mission today is to map out that entire journey, piece by piece. Understand the physics behind what we just call noise.
Okay, where do we begin? What's the absolute starting point?
It has to be vibration. The source material is crystal clear on this. No vibration, no sound. Simple as that.
Vibration being that rapid back and forth movement of an object.
Precisely. A quick oscillation.
And I like that the sources give us easy ways to, well, see this. It's not just theory, like the tuning fork example.
Yes, the tuning fork, classic.
You strike it, you hear the sound, but the moment you touch the vibrating prong,
The vibration stops, and poof, the sound is gone. Instantly.
that direct touch really confirms the energy is in the movement.
It does. And there's that water experiment described too, which is even more visual.
Right, touching the water surface with the vibrating fork.
You see ripples immediately.
Okay.
And if you push it in just a little.
Splashes, you actually see the water being thrown about. It vividly shows that physical shaking, the vibration, is what's launching the sound.
And this isn't just tuning forks, it's everything. Plucking a string, blowing air, scratching, even talking.
Our vocal cords vibrating. That's how we speak.
Or a bee buzzing that sound is literally its wings vibrating incredibly fast. It's the universal starting point.
Okay, so step one, we need something vibrating.
Yeah,
It's the engine creating the initial disturbance.
got it. Now, the next big question.
Yeah.
How does that vibration, that disturbance, actually get from, say, the tuning fork to your ear? Does the air itself travel?
This is where it gets a bit tricky, maybe counterintuitive. Sound absolutely needs something to travel through a medium.
Solid, liquid, or gas? It can't travel in a vacuum like light can?
But, and this is the key part, the sources highlight the actual particles of that medium, say the air molecules. They don't make the whole trip.
Exactly. That's crucial. When I speak, the air right near my mouth isn't flying over to you.
So what is happening then?
Think of it like a domino effect or maybe a Newton's cradle. The first particle gets pushed by the vibration,
Okay.
bumps into its neighbor, transferring the energy, and then, this is important, it bounces back to roughly where it started.
Ah, so it's the disturbance, the push, that travels forward, not the particles themselves.
Precisely. The particles just oscillate back and forth around their fixed positions. They ferry the energy along.
So sound is a mechanical wave. It needs that physical interaction between particles.
Yes. It's energy being passed through this chain reaction, this traveling pressure disturbance.
And it has a specific form, right? A longitudinal wave.
That's the one. The source material uses the slinky analogy, which is perfect.
Right, pushing and pulling the end of a slinky.
You see the wave move down the slinky, correct. But if you watch one specific coil,
It just moves back and forth along the same direction the wave is traveling, parallel.
exactly parallel, and that's what sound waves do in air or any medium, the particles oscillate parallel to the direction of energy transfer.
And this back and forth jostling in the air creates what? Like pockets of different pressure?
Precisely. Imagine the vibrating object, say, the tuning fork prong, moving outwards.
Okay, it pushes the air particles nearby.
It squashes them together,
Hmm.
creates a little zone where the particles are crowded, a region of high pressure and high density. We call that a compression.
Like a momentary traffic jam for air molecules.
Good analogy.
Yeah.
Then as the prong snaps back the other way,
It leaves a space, pulls away from those particles.
yes, it creates a region where the particles are more spread out, a zone of low pressure, low density. That's a rarefaction,
Compression, rarefaction, compression, rarefaction.
pulsing outwards from the source. That is the sound wave propagating. It's literally the movement of these pressure variations through the medium.
Wow. Okay, so that's how it travels. Now, how do we describe the wave itself? What are its characteristics?
We mainly use three key properties: frequency, amplitude, and speed.
Let's start with frequency. I know this relates to how high or low the sound is. It's pitch.
Correct. Frequency is simply how many of those complete wave cycles, say one compression and one rarefaction passing by, occur in 1 second.
Measured in hertz. Hertz.
Yep, and the link to pitch is direct. The faster the source vibrates, the more cycles per second, the higher the frequency.
And the higher the pitch our brain perceives.
Exactly. Think of a tiny piccolo flute versus a big bass drum.
The flute's sound comes from much faster vibrations, so higher frequency, higher pitch. The drum is slow, low frequency, low pitch. Makes sense.
Okay, next up, amplitude A. This one's about loudness.
How loud or soft the sound is.
Right. Amplitude is basically the size of the wave. It's how much the particles are displaced from their resting position during a compression or rarefaction.
So the intensity of that shove we talked about earlier.
Precisely. If you hit a drum softly, the vibration is small, the particles aren't pushed very far. Small amplitude, low energy wave, soft sound.
And if you hit it hard,
Big vibration, particles pushed much further, large amplitude. That wave carries more energy, sounds louder, and can travel further before fading out.
got it. Amplitude equals energy equals loudness, essentially.
Well, almost. There's a subtle but important distinction the sources make.
Oh,
Loudness is subjective. It's how your ear and brain perceive the sound intensity. It can vary between people. Intensity, on the other hand, is the objective, physical measurement. It's the actual amount of sound energy passing through a specific area per second.
so intensity is the physics, loudness is the perception.
You've got it. One is measurable with instruments, the other is our biological response.
And what about the third characteristic? You mentioned quality or timbre.
Yes, timbre. This is a really interesting one. It's why a violin and a piano playing the exact same note at the same loudness.
Still sound completely different. You instantly know which is which.
Exactly. Timbre is about the complexity of the sound wave. A pure tone, like from a tuning fork, is mostly a single frequency.
Simple wave.
But most musical instruments and voices produce a note. That's a complex sound made up of a fundamental frequency plus several other frequencies called harmonics or overtones mixed together.
And that unique mixture gives each instrument its characteristic sound quality, its timbre.
That's right. It adds richness and texture.
Okay, frequency for pitch, amplitude for loudness intensity, timbre for quality. What about speed?
Ah, speed. The classic example here is thunder and lightning.
You always see the flash way before you hear the boom.
Why? Because light travels incredibly fast, almost instantaneously for distances on Earth. Sound. Well, sound takes its time.
It has a finite speed, much slower.
Much slower. And importantly, as the source material points out, that speed isn't constant. It depends heavily on what the sound is traveling through.
The medium, right. And temperature affects it too.
Correct. Temperature plays a role, but the medium is the big factor. And here's the key takeaway. Sound travels fastest in solids.
Faster in solids than liquids, and fastest in liquids than gases.
Generally, yes. Think about air at room temperature, around 25 degrees Celsius. Sound travels at about 346 meters per second.
Quite pretty fast, but not instant.
Now, put that sound wave in a solid like aluminum. The speed jumps to, wait for it, 6,420 meters per second.
Wow, that's nearly 20 times faster.
Isn't that incredible?
Mhm.
It means the particles in a solid are packed tighter and interact more efficiently, passing that vibration along much more rapidly.
So the old movie trick of putting your ear to the railway track to hear the train coming actually works.
It really does. You'd hear the vibration through the solid steel rail long before the sound traveling through the air reaches you.
Amazing. Okay, so sound travels, it has speed. Does it bounce? That light?
It absolutely does. Sound reflects off surfaces, walls, cliffs, even water. It follows the same basic laws of reflection as light. Angle of incidence equals angle of reflection.
And that reflection is what causes an echo, right?
Exactly. An echo is just reflected sound reaching your ear noticeably later than the direct sound.
Noticeably later, the sources mentioned a specific time gap needed.
Yes, for our brain to perceive two distinct sounds, the reflected sound needs to arrive at least 0.1 seconds after the original sound.
A tenth of a second.
Right. And knowing the speed of sound, say roughly 344 meters per second at a typical temperature.
In 0.1 seconds, sound travels about 34.4 meters.
Correct. But that's the total trip there and back. So the reflecting surface needs to be at least half that distance away.
Which is 17.2 meters, roughly 56 feet. So you need a decent distance for a clear echo.
Precisely. If the surfaces are closer, or if there are many reflections happening very quickly.
Sounds blur together.
Yes, you get what's called reverberation. It's the persistence of sound in a space due to multiple reflections blending together. Think of a large church or an empty hall.
That booming, lingering sound. Architects have to manage that in concert halls, right? Using special materials or shapes.
Absolutely. They use sound-absorbing materials or design curved ceilings and walls to either diffuse the sound or focus it, depending on the need. Controlling reflections is crucial for good acoustics.
But we also use reflection intentionally.
We do. Megaphones or horns are designed to funnel sound waves using reflection, making them travel further in one direction.
And the stethoscope.
A brilliant example. It uses multiple reflections inside its tubes to channel the very faint sounds of a heartbeat or breathing directly and efficiently to the doctor's ears.
So reflection is both a phenomenon and a tool. Now, what about sounds we can't hear?
Ah, yes. Our hearing isn't unlimited. The average human ear can detect frequencies roughly between 20 Hz on the low end and 20,000 Hz, or 20 kilohertz on the high end.
That's the audible range, so anything below 20 Hz.
That's infrasound, very low frequency vibrations. We can't hear it, but some animals can.
Like who?
Rhinos communicate using infrasound, apparently down to 5 Hz. Whales and elephants also use these deep rumbles to communicate over long distances.
And the sources mention a connection to earthquakes.
Yes, this is fascinating. Earthquakes often generate infrasound waves before the main tremors that we feel. Animals sensitive to infrasound might detect this early warning.
Which could explain why animals sometimes seem to know an earthquake is coming before humans do.
It's a plausible explanation. Nature using frequencies beyond our perception.
And on the other end, above 20,000 Hz.
That's ultrasound. High-frequency sound waves, again, beyond our hearing range.
But not beyond other animals. Bats, famously.
Bats, dolphins, porpoises, they use ultrasound for echolocation, sending out high-frequency clicks and interpreting the returning echoes to navigate and find prey in the dark or murky water.
And incredibly, some moths can hear the bat's ultrasound.
Yes, an amazing evolutionary arms race. Moths evolved ears sensitive to that frequencies, allowing them to take evasive action.
Nature is just.
Oh.
Wow. So these unheard sounds, infrasound and ultrasound, they exist. Can we use ultrasound?
Oh, absolutely. Ultrasound has become incredibly important in technology and medicine, precisely because of its properties.
Like what?
Well, because it has such a high frequency, its wavelength is very short. This means it travels in very straight, well-defined beams and doesn't tend to bend around corners or obstacles easily.
Okay, so it's good for targeting specific things.
Exactly. Industrially, it's used for non-destructive testing. You can send ultrasound pulses into metal blocks, parts for bridges, machines, whatever.
To look for problems inside.
Yes. If there's an internal crack or flaw, the ultrasound wave reflects back from it much sooner than from the far side of the block. Detectors pick up these early reflections, pinpointing hidden defects.
That's clever, preventing failures before they happen. And in medicine.
Huge applications. Echocardiography uses ultrasound pulses to create real-time images of the heart beating.
So doctors can see the valves working, the chambers contracting.
Precisely. And ultrasonography is the broader term for imaging other internal organs. Liver, kidneys, gallbladder. It can detect tumors, cysts, kidney stones.
And of course, looking at a fetus during pregnancy.
A very common and safe use of ultrasound. It works by detecting the echoes bouncing off tissues with different densities, building up a picture.
Is it only for imaging?
No, it can be therapeutic too. High-intensity focused ultrasound can actually be used to break up small kidney stones.
Really? Without surgery?
Yes. The focused energy causes the stones to vibrate intensely and shatter into tiny grains, small enough to be passed out of the body naturally.
An invisible wave dissolving stones inside you. That's incredible.
It really is. Shows how understanding the physics allows us to harness these phenomena.
So let's recap this whole journey. We started with a simple idea. Sound needs vibration.
The essential starting point. That mechanical back and forth motion.
That vibration disturbs a medium solid, liquid, or gas. It can't travel without one.
Correct. And it travels as a longitudinal wave, a series of compressions, high pressure, and rarefactions, low pressure.
The particles wiggle back and forth, passing the energy along, but they don't travel the whole distance.
Exactly. The disturbance propagates, not the matter itself.
We describe this wave by its frequency, giving us pitch, its amplitude related to loudness and intensity, and its timbre or quality.
And we learned its speed depends heavily on the medium, being fastest in solids. It reflects, causing echoes and reverberation.
And finally, we explored the sounds beyond our hearing infrasound below 20 Hz and ultrasound above 20 kHz, with ultrasound having amazing uses in industry and medicine.
It's quite a story, starting from a simple clap and ending with dissolving kidney stones.
It really is. Okay, so for a final thought, something to really test our understanding of that core principle, the need for a medium.
Right. Let's use the most extreme example. Imagine you're standing on the surface of the moon,
Okay, spacesuit on, low gravity.
and your friend is standing just a few feet away. You decide to clap your hands together really loud, as hard as you can.
Right there on the moon. Given everything we've just discussed about how sound needs particles to push against each other, how it's a mechanical wave.
Would your friend hear that clap? Think about what the moon lacks compared to Earth, specifically regarding a medium for sound travel.
That really brings it home, doesn't it? The invisible story relies entirely on the stuff in between.